Okay, hello everyone. Many of you are actually working on this studio. Right now, I'm actually at home today. Unfortunately, I'm just not feeling too great this week, so was not able to make it into class, I'm afraid, but still wanted to make sure to go through the studio review. Actually, this is one of my favorite studios. This week we're going to be talking about the Sieve of Eratosthenes. It's a very complicated name for a way to find prime numbers. So the illustration on Wikipedia actually does a pretty good job of showing what we're going to try to mimic here. The idea is that we start off with a set of numbers that we care about. So we're going to find all the primes up to 120 in this example, and we start by just marking all of the multiples of 2 as not prime, and then all of the multiples of 3 as not prime. 4, etc., 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 until eventually, anything that's not been marked must be prime. So this is what we're going to try and sort of mimic in our code today. We're going to try and write code to make this happen. Whoops, looks like I forgot to import the studio here. Let me do that real quick. Usually I set this up ahead of time, but just forgot to do that final step. There we go. All right, we've now got our repository all set up. So if we go back to the instructions, it says first thing we're going to do is make a class. That's not an unusual place to start. We always need to make a class for our Java programs. Go ahead and set this up. I'm going to remember to check the public static void main checkbox this time. Sometimes I forget to do that, but if you forget, you can always just grab it from a different file, put it in there yourself. We need to prompt the user for some value of n, where n is going to represent this number or this number, depending on how you think about it. It doesn't really matter to me, whether you go up to and including n or not including n, as long as you're consistent. So to do that, we need to use our scanner. So go ahead and set that up first. N is going to be some integer, and primes only are relevant for integers. So and I probably should add a print message here. There we go. All right. So we are going to continue on by taking a look at some code to represent the items that we're going to sieve. We give you, the big fat hint that you're going to use an array for this. That's what we've been studying this week. But we need to think about what the structure of this array is going to look like. So there's a lot of different ways that you can use an array to solve this problem. We need to think about, what values are going to be in the array. We need to think about how big the array should be. We need to think about how we're going to use the index. The indices, remember, every value in an array has a position. So if we refer back to this picture, the two most common ways that I see are that we want to create an array of integers, and then we're going to fill this array of integers with all of the numbers up to n, including n or not, depending on what you want. And that's fine. You can do that. Or we could, I think an alternative approach is to recognize the fact that each of the numbers that I'm looking at on the screen here are either prime or not prime. So if I look at one of these values, I can say that 65 is either prime or not prime. In this case, we know that it's not prime. But to me, that strongly suggests that we could use an array of Boolean values here. The reason that we can get away with doing that is because, if we have an array of Booleans, we can use the index to represent the value that we care about. So this would be actually showing us a picture of our array. So if I look at the position 2, I would see either true or false there, indicating whether the value 2 is prime or not. Same for all of the other values. If I look at 76, I'd see either true or false, which tells me whether 76 is prime or not. And so to accomplish this action of determining what numbers are prime or not, it's just as straightforward as, starting with all the multiples of 2 and marking them as false, right? Assuming they're all true to begin with, we're going to go through and mark them all as false, and then any values that have not been marked false by the time we're finished should therefore be prime. So that's what we're going to try and do. That's the method that I prefer. Either way, though, so several people or several groups like to approach this with an integer array. I really like the Boolean array approach, so that's what I'm going to use here. And when creating our array, we have 2 ways to do it. So the first way to do it is the way that I've shown you here, where this is going to create an empty array for us. The contents of the array are perhaps unknown. We could take a peek and see what's in there for a second, but the other way that we could do this, if we know what we want the values to be, we can use this curly brace syntax, and then we specify what we wish the contents of our array to be, the starting values of our array. Otherwise, it's just going to use that default value. So we do need to specify a size, and it's probably going to be based on n somehow. So okay, we'll plug n in as the value. We also have to recall that the array index starts counting from 0, not 1. So if n is 10, that means the index of the last value is going to be 9. Let's take a moment just to check and see what the default value is in our array. Just because I'm interested, I'll enter 10, and the default value is false. Okay, so that actually is an issue for us, right? The way that this code works is, the way that I want this code to work is assuming that all of these values start marked as true, and then I'm going to go back through and mark the ones that I know not to be prime as false, leaving all of the remaining ones marked as true. In fact, if you scroll a little bit farther down on this page, you can see that there's instructions here on how to work through this, written out in sort of English. But then if you scroll down a little bit farther, there's an example, and then even farther still, we see an example given to us in pseudocode. So this is code that is not written in a particular programming language. This is not Java, right? This is not Java code or Python code or any language, but it's written kind of like computer code, and it's close enough to computer code that a programmer would be expected to be able to look at something like this and translate that into Java code or Python code or whatever language you're interested in performing this little exercise in. So let's go ahead and start maybe trying to do that. And one way you can do that is even trying to write out little comments in the code for what you want to do that kind of match up with the pseudocode here. We can see, all right, the input is an integer n greater than 1. We already have that. We use our scanner for that. Output's going to show us all the prime numbers from 2 through n. Let array be an array of Boolean values. There we go. That's a good choice. Indexed by integers, 2 to n. Well, ours goes from 0 to n, so that's a little bit of a place where we deviate, but that's okay. Initially all set to true, and we've seen that the default value is false, so we actually have some work to do here. We need to go through and set all of the values to be true. So let's go ahead and do that next. If you worked through the prep work, watch me speak about the prep work this week, you know that the loop that I'm writing right now is a very common type of loop that you're going to see used with arrays. So the fact that I'm using one here is probably not terribly surprising. You could argue that we don't need to start I from 0, and we could start I from 2 because we don't care about the values less than 2 for the purposes of this exercise, and that's okay. I actually would agree with you. I also don't think it's that big of a deal to start I from 0 necessarily, at least not in this particular case. But what we want to do within this loop is to set all of the values to be true. So we're not actually doing the quote-unquote prime search yet. We're just setting up our Boolean array such that all of the values start to be true. Start out being true. So you can already kind of see some of the deviation here, right? The way that different code gets input, or the way that different languages provide input is different. The way that you set up arrays is different in different languages, but we know what the concept of an array is. We know what the concept of an index is. We know how to set the array values to be true. And if we look down here, you can actually see this looks very much like a for loop and an if statement. And that's very intentional, right? These can very easily be translated into for loops and if statements. That is very much the desired outcome. So let's see if we can do that. We can see that it's not written like the for loops that we're used to looking at, but we can sort of translate it. So if I is going to start at 2, it looks like it's counting up by ones, and it's not going to exceed the square root of n, which is an interesting stopping point. Let's see if we can write that loop. I is going to start at 2. I is going to be less than. So in order to generate the square root, we have to use the math library. So I'm going to go ahead and refer to the math.squareroot method here. We're going to go up to the square root of n being the upper bound on primes that we wish to find, and then incrementing I by 1. Okay, so we've accomplished that loop. If I take a look at the next part of the pseudocode, we're taking a peek at this if statement. If a at I is true. Think about what that means. That means that we currently believe this value to be prime, right? We can actually leave this step off and it won't really affect the outcome. There's actually, you know, something to be said about using the square root of n as a stopping point as well. I think this isn't necessarily the place where most people would land for this loop. I think a lot of people maybe would use n over 2 as the stopping point here if we're checking all of the multiples that we need to check. Or perhaps even n if you want to be, you know, extremely cautious, but that's going to involve some redundancy. It has been, you know, shown, proven, that you only actually need to go up to the square root of n here for this sieve to work. I'm not going to show you proof of that. This isn't the kind of class where we do those kinds of things, but, you know, you're welcome to come in and chat with me about office hours sometime if you're interested in getting more of the background information about this particular problem. I'm actually going to skip this if statement for the time being and maybe come back to it for a second. This part of the pseudocode right here is the trickiest part. So if we think about what this for loop is going to do, this is the one that's actually trying to set the multiples. So the way that it's written, it's creating a loop variable j, where j starts out as I squared, and then it's going to go to I squared plus I squared plus 2I squared plus 3I. So these are multiples. It's incrementing the multiples. So if I is 2, it's going to go 4, 6, 8, 10. If I is 3, it's going to go 9, 12, 15. So we're going through and checking all of the multiples for these values of I, and then setting the Boolean values at those positions to be false, indicating that those values are not prime. Those values are not prime. We've proven that they are not prime by generating the multiples. So let's go ahead and stick that in to our code. Remember, we're using another for loop here. We're going to create our loop variable j, which is based on I. So we're starting it out at I times I, right? J is going to be less than, what is the stopping point given here? Not exceeding n. Okay, that makes sense. J is less than n. J plus plus. And then finally, we're going to just set the sieve of j to be equal to false. So j being the value that's going to represent the multiples that are being computed. Okay. So the last thing that we need to do is we need to have some way of checking our answers. So we need to have some way of verifying that we're actually getting the correct primes here. But let's go ahead and come down to the bottom and recognize the fact that once this little section is done, I'm hoping that all the non-prime numbers will be marked false. So all I need to do then is go back through the array one final time, look at, see what values are still marked true, and just display those values. So let's go ahead and do that one final time. I'm going to go ahead and say for int I is equal to 2, that's our first value. I is less than n, I plus plus. If sieve at I, you could also say sieve of I equals true, but actually I want you to consider for a second that You don't need to put the equals true on the end. Then you could just leave this as civ of I because this contains a Boolean value. I. Okay, we're just going to print it out. Let's give this a go, see if we have any problems. It's entirely possible. They've got some mistakes. The example we saw online was 121, right? So, yeah, obviously we have some issues here. Oh, I see what the problem is. It's right here. I didn't follow the script. So if you look at this loop here, this tricky loop that I said, it says it's going up by multiples, right? By multiples of I. So the loop that I've written does not reflect that. This actually is just incrementing j by 1 each time, but that's not what should happen. If I is 2, j should go up by 2 each time. If I is 3, j should go up by 3 each time. In other words, we wish for j to go up by I each time. That was a mistake. I was marking a lot more values false than what I should have been. So let's try our code one more time and see if fixing that value helps. Oh, there we go. That looks a lot better. I see 2, 3, 5, 7. Those are all prime. 11, 13. Yep, good. I think this is right. I think these are all primes. We can actually even double check with our good friend on Wikipedia if we wanted to. 113 is their largest prime that they have marked. Yep, that matches our list as well. I think this works. I think this works. This is also a really interesting problem for, a few other reasons, right? So if you're looking for a reasonable solution to this problem, here it is. I like this solution a lot. If you came up with something, reasonably approaching this during the studio today, then I think you should be very happy with that outcome. Let me talk though just about a few other issues with this problem, a few other things to consider regarding this problem. One common way that I'll see people try to approach this problem, instead of using multiples, they'll try and use division instead. So they'll try to look at each number and ask if it's divisible by 2, divisible by 3, divisible by 5. So it's kind of the opposite of what I'm doing here. Instead of looking at a number and saying this is not prime. That's what I'm saying here. I'm making a statement. I'm going to the values, each of these values is saying you're not prime, you're not prime, you're not prime. If you're trying to use division or modulus to be more accurate, is the classic sign that you're trying this approach. If I see something in your code, that says if this value mod 2, mod 3, mod 5, mod 7, there's a few different problems with that approach. So one common issue that I see with that is that you're going to be checking modulus on a lot more values than you need to be. You're checking a lot more divisions than you are by generating these multiplications. You're going to have a lot of if statements in there where you're doing a lot more redundant checks to see, does it compare against this prime, this prime, this prime, this prime? I have to check a lot of different prime numbers just to see if one value is perhaps prime or not. Whereas here, I'm just computing multiples, right? And marking them directly. I'm not asking the question. I'm being more direct. I'm saying you are not prime. It's going to be faster. It's going to be more efficient. But even logically, right, using modulus does not work. So I want to be 100% clear that using modulus in your solution here is not acceptable. Because even if it works up to 120, I could ask you to then generate all of the primes, up to 1,000. And you may have to add a few more prime numbers onto your little list of modulus checks to make it work, but perhaps you could. But then I'll say, all right, give me all the primes up to, 1,000,000. And then your list isn't going to work anymore. You'll have to add more primes to it, and we can keep playing that game to infinity, right? So it's just not practical. It's not a good solution here. My argument is that the solution I've written here is going to work no matter what, right? It's not going to suffer from that same issue. And we can reinforce that even more by the idea, going back to that if statement from the pseudocode, this idea that, we have a list of prime values already. So actually, the only multiples that I need to check are prime numbers. So I don't even need to run this innermost loop unless I think that the value of I is perhaps prime. In other words, this value is still true. It hasn't been marked false yet. Including this if statement, I want you to notice, should not affect the correctness of the program. So our program is still just as functional as it was before, right? But what you may notice, and I might even be able to show you this with a little bit of clever work here, is that it should work faster now. So one thing to consider is that by including all of the values, I am marking some values more than once. So I mark you false, and I'm going to come back again and mark it false again for a different multiple, right? I want to avoid that double marking. That's a waste of time. That's a waste of time and energy on my part. And you can actually see that, if you type in large values of n, you'll see that the code is going to stop being able to respond eventually in a reasonable amount of time. Although I'm getting up to 7. That's 10 million. So yeah. There we go. You can start to see it out with 100 million, and that's a lot of values as well. I'm not so much concerned about the printing. That's always going to take a long time. There's just a lot of values to print. But you can actually see the noticeable difference at the beginning with the computation when I run this. Let me show it to you one more time. If I do it with, you can actually, or even with 9 zeros, no, I'm going to do it with 8 zeros. 8 zeros after the 1. You can see there's a noticeable amount of time that it takes to compute. That little, second or so. If I take this if statement out, however, that's going to involve a lot more marking. So repeated marking of values that don't have to be marked. So if I run the same exact you can see that for the same exact value that I got before, it still got me there, right? But it took a noticeably longer amount of time. Just by removing that if statement or including that if statement, I've improved the efficiency of the code. I've optimized it a little bit. I've made the code work exactly the same way as it did before, but now it's even faster. It's even more efficient. This is really at the heart of computer science. This is sort of, the true study of computer science, not just how do we write code to get the job done, to make things work. Of course, we do care about that. It's very important to us. But we also care about efficiency. We also care about getting it done in a reasonable amount of time. I mean, there are some problems that are flat out are not computable unless we are very conscientious about how we approach those problems. They become too big to solve, unless we come up with clever ways of approaching those problems that don't overtax our computing resources and take too long. So you can already start to see that even in these simple examples that we're showing you in class with prime numbers, which turns out is actually a very useful thing for us. Prime numbers are used in cryptography all the time, and prime number hunting is a thing that happens. But the prime numbers that they're searching for are so large that it's not really enough for one computer anymore. But that's sort of besides the point. Anyhow, there are other optimizations that you could, I think this code is pretty close to the pseudocode given on Wikipedia. If your code wasn't super optimized, running at the fastest possible speed, that's not really the point of today. It's just sort of an interesting little thing I wanted to show you related to this particular studio. Okay. So that covers, I believe, the studio itself. I just wanted to take a moment then to talk about the assignment for this week to wrap up the studio review. This is going to be broken down into, I believe, 3 different puzzles. Yeah, so we've got 3 different puzzles for you to work on this week. The first one is sorting an array of values. And so this is very much related to what we were just talking about. I'm giving you some pseudocode here. I'm actually giving you, this is not Java code, right? But it looks kind of like code. You can see some code-like things in it. So look at this and turn it into Java code. That's your task for the first problem. I linked you to the Wikipedia page for pseudocode if you want to look at some more information about what pseudocode is and how we use it. It certainly won't be the last time that that concept shows up in this class or in your other comp sci classes. The next problem is this idea of a frequency table. So you're going to generate values between 1 and some user supplied maximum value. So I want to see 100 numbers randomly generated between 1 and 1,000,000. So you're going to go off and generate those 100 numbers. Maybe you're starting a new lottery or something like that. And then I want you to count how many times each of the values pops up. So here's a more realistic example, choosing 100 randomly generated values between 1 and 10. If in an ideal world, right, we would see each one of these picked exactly 10 times. That would be a true, flat, random distribution. And sometimes you might be able to see exactly that, right? But more often than not, you're going to see that, okay, some values are going to be a little bit bigger than 10, some are going to be a little bit smaller than 10. But on average, they're all going to kind of center around 10. And that is, in fact, what we see here. The big thing to keep in mind with this part of the assignment is that this should be done using an array. This part here is very much like what we saw with the sieve, where this to me looks like the index, and this looks like the value. So in the problem we were just looking at on the studio, we saw that the index was used and the value was a Boolean variable. But here the value does not look like a Boolean. It looks like something else. I'll let you figure that out. It should be pretty obvious, I think. And so the idea of counting as you go to this index and then make another tally. Go to this index, make another tally. This is a very common technique. This is sort of a basic approach to a very common technique that we use arrays for. And then last, to get some two-dimensional array practice, I want you to create a program that's going to generate symmetrical images. So you are going to ask the user to type in values for n and m, which represent the dimensions. They do not have to be the same. I think it's important to note that it should work for any positive values of n and m, right? And then you're going to randomly generate points. Consider, like we saw with the pi example last week, to generate a point, you're going to need two values, one for x and one for y. Those values are going to be indexes into a two-dimensional array for this problem. So yes, you're going to generate those values. You're going to have to think about how to do the symmetric part. So if you generate a value, if you randomly pick a value on the left, you have to figure out where its corresponding value is on the right. To figure this out, I would encourage you to get out a sheet of paper or a whiteboard and write down the indexes and see if you can figure out what the math is, right? If I pick this number over here, what number should I be picking over here? And then see if you can figure out what the pattern is, right? See if you can figure out what the pattern is. Turn that into code. Okay, well, that's going to wrap it up for the studio review and the assignment review. And just in time, here is my good friend Franklin. Stop by to say hello to all of you and wish you good luck on this week's assignment. I hope you all have a great weekend, and hopefully I'll be feeling well enough to be back in class in time for next week, which is a big week for us. We have the first exam coming up. So hopefully I'll see you all in McDonald 162 on Tuesday for our exam review sessions.